Welcome to a Zynq 7000 PCI Express Root Complex Made Simple Quick Take video. In this video, we'll show you how to set up a PCI Express Root Complex in a Zynq 7000 device so that it can communicate with an off-the-shelf PCIe to USB 3.0 card. First, we'll look at setting up the Zynq 7000 device using the Vivado IP integrator tool. Next, we'll show you how to set up Linux using Xilinx's PetaLinux tools. After that, we'll use the Mini-ITX board from our partner Avnet, as it has a PCI Express slot that we can use. Finally, we'll show you how to read and write using a standard USB flash drive from the Linux OS running on the Zynq 7000 device. Let's get started. First, we'll create a project. I'll give it a name and select the appropriate device on the ITX board, which is the Zynq 100 in my case. They also provide a 45 version. Create the block diagram. I'll call it Root Complex as a fitting name. First thing I'll do is I'll source a TCL file that will place down the processing system with many of the options needed to work on the ITX board. So for example, we're going to need the DDR, it's going to use that, it's going to use the SD card as well. And it also set up a lot of the interfaces that we're going to use too. For example, the HP and the GP ports. So now we'll add several of the blocks. We'll add PCIe and an interconnect. We know that PCIe will need to touch the system's DDR, so we'll provide this data path. Then we also know that Zynq needs to set up the PCIe controller and also needs to communicate with the downstream device. So we'll set up these two interfaces. Make sure that the bridge is set up for root complex, otherwise it's set up as an endpoint. And this supports by 4 Gen 2, so we will go ahead and set it up for that. We'll set the bar range to be 1 gigabyte. Notice here the data widths are 128. And we'll go ahead and set the class code here as well. This will allow it to link to the AXI PCIe driver. These signals are the SerDes lines. We'll make them external as they need to be top ports. And now let's connect the reference clock. We'll need to set this to be an iBuff DSGTE and connect that to the reference clock. And then the inputs need to come from the board, and they do on this ITX board. We'll give them a fitting name like ref clock. And now we need to add the reset controller. Also acts as a synchronizer. We'll connect that to our AXI clock that comes out of the PCIe block. And then also make sure to give it the locked signal, that way it comes out of reset appropriately. So we'll call the first N will be the system reset from the board, and we'll have that be the reset for all the blocks. And these process system resets are going to synchronize it for us and also give us the appropriate order that they need to come out of reset. Make a copy of the same thing and do it for the other clock that comes out of the PCIe bridge. Make the auto connections. This makes them a lot faster than how I can wire them. And then the interconnect output will connect to the main resets of the interconnects, and then the peripheral resets will go to everything else. Then we'll take a look at the tie-offs and make sure that any input port has a tie-off if it's not connected. Lastly, we'll connect the interrupt line from the PCIe controller to the Zynq processing system. We'll go ahead and make the DDR pins external and the MIO external pins as well. Now let's take a look at the address map. Looks like there are some unmapped addresses, so I'll go ahead and click the auto button and see what gets mapped. Looks like one of them didn't get mapped, so it's because one defaulted to 1 gig. I'll go ahead and make it smaller, 256 meg, and then assign the other side. The controller here, I'll go ahead and give them random addresses, and for the size of the controller I'll set it to 64 meg. There is a range that needs to be, and 64 does lie within the range. And then here we'll map this to 6 so it matches what the address editor was set to. We'll save the block diagram and validate. Make sure there are no violations. And now we will generate the HDL wrapper. We'll let Vivado manage it because we don't need to make any manual modifications to the file. If you did want to make manual modifications, you may not want to let Vivado manage it. Next, we'll add the constraints file. And here I labeled it ITX_placement.xdc. We'll look at this constraints file and notice there's only 2 constraints there. And I'll show you how I got those 2. One was for the reference clock location, and the other one was for the reset location. And that's where I got it from the zboard.org website. And here you go to the downloads section, and you'll find that there's a master XDC file, and this is where I found the constraints. We'll go ahead and close the block diagram and synthesize the design. After synthesis, we'll take a look at the timing constraints, make sure we don't need to add anything. It does estimate a challenging path, but we'll see if it meets timing with the placement algorithms. If I go to the check timing section, this is where I was mostly interested in. Looks like there are no unconstrained internal endpoints, and the only input delay that's missing there is for the reset line, so we can ignore that one since it's synchronized internally. And now we'll go ahead and generate a bit stream. Now that a bit stream is generated, we can export the hardware definition file and include the bit stream as well. I'm going to change the location so that it's in my PetaLinux area, just to make it easier to access. And now that it's exported, we can close Vivado, as we will need to start working with the PetaLinux tools. Go ahead and change directories into the PetaLinux directory that I created. But before we do any PetaLinux work, we will first need to grab a specific checkout from the Git repository for the device tree, as there is a known issue with the device tree with the PCI Express bridge. So I'll create a directory, call it my device tree. Also create an EDK user repository directory, and within there we will grab the new device tree. First we're going to clone the current one, and then we will cd into there and check out the 2014.2.01. This will get checked into the master branch for 2014.2. Now that it's downloaded, we can go ahead and get started with PetaLinux. I'll source the settings script so that it's set up to run, and first we'll create a PetaLinux project, call it PCIe root. I'll cd into the directory it made, and then run petalinux-config, and I'll grab the HDF file that I created from the Vivado tools, and I'll also point to the device tree that we made. That way it creates an accurate device tree for us. And here I will also set up the boot settings. That way I will boot from the SD card. Then I'll do petalinux-config and set up the root file system. Here I'll add the PCIe or the PCI utils so I can run lspci. And then I'll run petalinux-config one more time, but for the kernel this time. And this is so that I can enable the XHCI drivers. And that driver is necessary for this particular device, which is the USB 3.0 card. Now I'll run petalinux-build. This will build the U-boot, the kernel, the device tree, and the root file system for us. And now I will run petalinux-package, and this will package everything up for us. It'll package the FSBL file, the U-boot, or FSBL, U-boot, the bitstream, all, and Linux, so that we can place those images, in our case, onto an SD card. And here I'll grab the image.ub file, copy it locally here. That way we can take a look at both files. The two files I'm interested in here are boot.bin and image.ub. I'll copy those over into a shared folder of mine so that I can grab it on my Windows machine, copy it over to the SD card. And I'll take that SD card and I will plug it into the the Mini-ITX board. I'll plug in the endpoint. Connect the USB for the UART connection and power it on. Here we see Linux booting, and we'll log in. The default password is root. We'll run an lspci-vvv, and notice here that's the endpoint. So it has been detected, and now we'll go ahead and plug in the USB flash drive. You'll see it shows up here, and just to verify, run a dmessage and notice that it's SDA1. And then we'll go ahead and mount to that directory. And I'll CD in there. I'll take a look at the files. I have a hello linux.txt file. And I'll go ahead and I'll modify this file. So we'll see we're doing both reads and writes from the USB card. We'll CD out of it and then unmount. And now we can unplug and look on our local PC and take a look at the file we just modified. And there you go. Hope you enjoyed the video, and hopefully this will allow you to explore the other options that you have with the PCIe root complex.